We're going to talk today. So my name is Brandon Lawton. I'm another astronomer at the Space Telescope Science Institute in the Office of Public Outreach. And I'm happy today to talk to you about Hubble's views of the deep universe. So we're really going to get into some cosmology, some deep images of the universe, and we'll talk about what that means. So can we go ahead and turn the lights down? And so I may have to do the clap thing again if I start to see people. Yeah, I know. But these images really do a lot better if you can see them more clearly. So first thing we want to talk about is the way that I like to tell the story is I like to make sure that we start from the same foundation. So we're going to start down here at the galaxy level. We're going to talk about what is a galaxy. Now this is an image that Frank showed earlier. This is Robert Hertz's illustration of what our Milky Way may look like. Okay. So here's our galaxy, what it may look like, right? And of course, what are galaxies? Well, galaxies have lots of things in them, right? They're made up of planets and moons. So I put, here's where our solar system is located in our galaxy, okay? But we now suspect there's billions of planets in our own galaxy, right? So galaxies are comprised of planets and moons. They're comprised of lots of stars, okay? You can see just from this image that stars come in lots of different colors. Okay, you can see there's red stars, blue stars, right? So galaxies have lots of stars. Our own galaxy has hundreds of billions of stars. Okay, all right, and gas and dust. Actually, some of my favorite stuff. Gas and dust plays many important roles in astronomy, and there's lots of gas and dust in galaxies, and these. We'll talk about, these are locations where, this particular location is a location where stars are being born, but there's lots of different types of gas and dust in galaxies. Okay, so that is a galaxy, right? Now here is the Earth. All right, now I want to play, we're going to talk about how do we study galaxies in the universe? How do we know some properties of galaxies? But let's take a step back and let's do a thought experiment, okay? Let's say that you are an astronaut floating above the Earth, right? And you have no other way of communicating with the Earth, but you can only observe the Earth, okay? And you want to do an experiment. You want to learn everything there is to know about humanity, okay? What would you do? You want to know how people are born, how they die, you want to know the varieties of humans on the Earth. What would you do? What was that?
I said bless you to her.
Oh. You bless you? I thought I heard someone say it. What would you do? It's a thought experiment. It's just thoughts. We're not actually doing the experiment. Don't worry, we won't waste billions of dollars. Some ideas. What would you do if you're stuck up there and you wanted to learn everything there was about humanity? What would you do?
You're going to observe them.
Observe them. Okay, so what do you mean by that?
Look at them, whatever tools you have available to you.
Okay.
Telescopes.
Okay. So use telescopes, maybe take pictures. Okay. All right. Well, let's say we did that. Okay. Here's a picture of a girl. Looks like on a beach. Okay. That's great. We did that. Does that tell us the full variety of humanity? No.
Take a lot of pictures.
Oh. Okay. Let's take more. All right. We're starting to see that there's more variety. We're starting to see that humanity comes in multiple flavors, multiple ages, and all sorts of things. Let's do it again. All right, we're starting to get more of a picture. Let's do it again. Okay, you can see that, one thing you can do, right, is in lieu of following lots of people from birth to death, which is very impractical, right? What you can do is you can take lots and lots of pictures and you can build up a story. A statistical story. It's statistics. You don't know anything about any individual person, but you can build a statistical story of humanity, of the varieties of people on the Earth. Okay? This is basically what we do with galaxies, right? We can't follow a galaxy from birth all the way through its life. That would take billions and billions of years, right? But galaxies come in many different varieties, many different flavors. And all we have basically are the pictures of them, the light that comes to us from them. Okay? So if we want to learn all there is about galaxies, the shapes, the colors, the sizes, we have to take pictures of them, lots and lots of pictures to build up that story. Okay? So that's what astronomers have been doing for a long time in the nearby universe. We've been taking pictures of galaxies. And in the local universe nearby, and Frank was talking about the local universe nearby, we see that galaxies come in 3 different flavors. They come as spirals. We were talking about spirals, right? Like the CD shape, the disc shape. They come in these ellipticals, which are more spheroidal or football shaped, right? And then basically the everything else bucket. Right? If it doesn't fall into those 2, it follows in the everything else bucket, the irregular galaxies. Okay? There's no value judgments. It's just that they don't follow those other 2 shapes, right? So there's these shapes in the local universe. What you'll notice offhand is when you look at these is that, and what astronomers have noticed is that these galaxies, not only do they have different shapes, but they have different colors. Okay? I showed you a picture of stars in our Milky Way earlier that had the stars were many different colors. Okay? A lot of the colors we see in these galaxies, right, come from the fact that those stars are different colors in those galaxies. So in spirals, we tend to see that the central part of spirals, the bulge here, tends to be orange because there's lots of orange stars there. Okay? And incidentally, that typically means that they tend to be older stars. Okay? Older stars tend to be redder or oranger. But we don't have to talk about exactly how we know that, but just so you know that there are orange stars in the center, and in these spiral arm structures, you can see that the stars tend to be bluer. Okay? In ellipticals, you tend to see very few blue and lots of orange. And in irregular, you tend to see a variety, but oftentimes some of the bluest galaxies are these irregular galaxies. Okay? So we can learn about shapes by looking at galaxies in the nearby universe. We can learn about what their colors are. We can start to do some physics and try to understand what those colors are telling us, which they tend to tell us sort of what types of stars are made up in these galaxies. So as it turns out, blue stars tend to be young. They tend to be massive stars. They don't live very long. And so when you see blue stars, because they don't live very long, when you see them, you know that they're young. Okay? But they tend to die off, and the ones that stick around for a long time are the orange ones. Right? So there's very little star formation, current star formation going on in ellipticals, lots of star formation going on in the spiral arms of spirals, which give you that blue color and so on. So you can learn a great deal just by looking at shapes and colors and so on. Okay. Now, I'm going to go through, that's great, that's the local universe, but we want to learn more. We want to take more pictures and learn more. So what are the galaxies like in the deep universe when you look really far away? Okay. This was actually a program that was started in 1996 by Dr. Bob Williams here. He was the director of the Space Telescope Science Institute at the time. And a lot of people don't realize this, but when you want to get time for the Hubble Space Telescope, okay, which this was done, it's a very expensive telescope and it's a very popular telescope. And the way it works is astronomers write scientific proposals for what they're going to use the telescope for, how much time they need it, what is the scientific purpose, and so on. And all that to say is that the proposals, Hubble is oversubscribed 10 to 1. So for every 10 proposals, maybe 1 gets it. Okay? So it's not easy to get time on Hubble. What Bob decided to do, now Bob is the director at the time, anyway, he was the director. What he decided to do, so the director gets this other bucket of time to use Hubble called director's discretionary time. What the director typically had done up to that point was use it to do observations that just didn't make the cut in the proposal process. Okay. What he decided to do was something very different. He decided that he was going to do maybe one of the most basic science experiments you can think of, which is find a really super empty patch of sky, point Hubble at it for 10 days and stare. Okay? Very basic. What are we going to find? This was not popular. Well, it was not popular for a lot of astronomers. It was oversubscribed 10 to 1, and he's using very valuable time to just sit and stare at space at an empty patch of sky. All right. So at the time, this was quite audacious plan. What it turned out, though, was maybe the most significant Hubble image ever taken, which is the Hubble Deep Field here. Okay. Almost every, what we found after 10 days straight of observing was this. Almost every little thing on here is a galaxy. Okay. Even the little smudges you see are galaxies. The only things not galaxies on here are these few spiky features. These are stars that are in our own galaxy that we're looking past. So there's a star there, there's a star there. There's only a few stars in the image, but everything else is a galaxy. So there's about 3,000 galaxies in this image. To give you some idea of the size scale on the sky, you might think, okay, 3,000 galaxies, that's not that crazy. Well, again, it was at an empty patch of sky. The size scale is the same as if you took a dime held at arm's length. Okay? It's the eyeball of FDR on the dime. That's what this patch of sky corresponds to in terms of scale. That small patch of sky for 10 days straight. And we got this, the Hubble Deep Field. And this was actually quite mind-blowing. In fact, if you ever decide to Google the most important picture ever taken, not the most important Hubble picture, but just the most important picture ever taken, usually what comes top of the list is one of these Hubble Deep Fields. Okay? We can all debate if that should be there. But just to give you some idea that this is one of those groundbreaking experiments where we started to put things in context. We started to see how big the universe really was, where we could stare at this really deep empty patch of sky and get so many galaxies. Okay, well that was just the beginning. 1996, again, Hubble launched in 1990, so Hubble's been around 25 years now. This was in the first decade of Hubble's life, and this experiment started, and it's been going since. So 1998, they redid the experiment, and they pointed at a different patch of sky. The first one was in the northern hemisphere, and a patch near the Great Dipper. This one was in the southern hemisphere, the Hubble Deep Field South. Again, Bob Williams was the director. About the same instrument. You can see it has this funny shape, the instrument, but it's the same instrument, but this time in a different patch of sky. Again, remember, we wanted to take pictures of people in lots of different locations because we wanted to see the variety. We didn't know at the time if the Hubble Deep Field was an unusual patch of the universe or if it represented the normal universe. So we wanted to take more images. So we did the experiment again. We got very similar results. Roughly the same number of galaxies, about 3,000, very similar results. Okay, but that was with the same instrument. Okay, then what happened to carry this Hubble Deep Field story further was in 2004, they decided to do the Hubble Ultra Deep Field. Now you know the Hubble Ultra Deep Field is better than the Hubble Deep Field because it's ultra, and ultra is just more awesome, right? I mean, it's in the name. So it's ultra. Okay, why is it better? Well, the reason it's better is because we've had servicing missions to Hubble. Okay, Hubble now is better than it has ever been in its lifetime. And the reason is because we've had 5 servicing missions. 5 times astronauts have gone up. They've not only repaired Hubble, but they've made it better. And the way they've made it better is they've taken out old instruments, old detectors, old cameras that were less sensitive and put in better cameras that are more sensitive. And that's what they've done here. This is with a new camera that is much more sensitive. So for the same amount of duration, you can see deeper in the universe because you can see fainter objects. It's more sensitive. It can capture more light. And they did this, the Hubble Ultra Deep Field. This one is also in the southern hemisphere, a whole different patch of sky in the southern hemisphere. About the same scale on the sky, about the FDR's eyeball, held at arm's length from the dime. About the same scale. About a day longer. So the first Hubble Deep Field was about 10 days of exposing straight. This is about 11. So it's comparable. But instead of 3,000 galaxies in this patch of sky, they saw deeper and they saw 10,000. Okay. So this patch of sky, they saw 10,000 galaxies. Okay. Now we're doing something. Now we're starting to get a lot of variety. We're starting to get the numbers of galaxies. And this is again to tell you sort of the size scale. Don't worry about what XDF means, but this is basically the Hubble Ultra Deep Field, the scale of it relative to the full moon. The full moon is about a half a degree on the sky, and the XDF or the Hubble Ultra Deep Field is about, I think it takes about 15 or so of them to cover. Now, this actually looks much bigger. If you actually go outside and look at the full moon, you'll notice that it actually looks, because it's blown up on the screen, the full moon actually looks smaller than this on the sky. And you can go out and you can imagine it would take 15 of these Hubble Ultra Deep Field images to cover the full moon. Just to give you a sense of scale. You can do, and this is a very fun experiment you can do with your kids, right? And we have this available on Amazing Space. It's an online exploration called the Hubble Deep Field Academy. So you can go on Amazing Space and actually find the materials for this. But if you do the experiment, right, you say, okay, if you take the Hubble Ultra Deep Field and we know the size that it covers on the sky and we know the number of galaxies in that image, how many of those images, how many Hubble Ultra Deep Fields does it take to cover the whole sky? If you know how many images it takes to cover the whole sky, and you know how many galaxies are in just one image, you can calculate how many galaxies there are in the observable universe across the whole sky. That's assuming that the Hubble Ultra Deep Field is a typical patch of the universe, right? That it's no more populated with galaxies than any other patch, right? That's the assumption. But if you do that assumption, you can do that calculation. As it turns out, it would take over 12.5 million HUDFs to cover the whole sky. Okay? So you'd take that number and you multiply it by 10,000, okay? And the number you get is several hundred billion galaxies, okay, in the observable universe. Remember, each galaxy has likely billions to hundreds of billions of stars. Okay, so there's trillions of stars in the observable universe, likely probably about that number of planets in the universe. Okay, again, this is getting to contextually the scale of the universe, putting our place as humans in the scale of the universe, right? How massive the universe is and where we are in it, right? Okay, so let's take a look at the Hubble Ultra Deep Field, and we'll just do some. These are just little individual cutouts of the Hubble Ultra Deep Field. And this is just to show you, now, again, this spiky thing's a star. So that's a star in our own galaxy that we're looking past. So that doesn't count as a galaxy in the Hubble Ultra Deep Field. But all these other things are galaxies. And what you'll notice is that they cover a variety of shapes and colors. Okay, so we can start to learn something. We can start to do binning population things. One of the activities in the Hubble Ultra Deep Field that you'll find is a very simple, essentially counting exercise, which is a basic scientific exercise where you say, how many orange things are there? How many blue things are there? How many spiral-shaped things are there? How many irregular things? You can do those simple counting things, and you get interesting scientific results by doing that, and you can do that with your students. But you'll notice that we have things like on the upper right, we have this spiral galaxy, which looks something like a galaxy that's kind of what we might expect as a spiral in the nearby universe, in the local universe. But as you look deeper, you'll notice that you get some weird shapes that are just odd. Okay, so you're starting to get some really odd, distorted shapes that would not fall under. They would definitely fall under the irregular category. They would not fall under the elliptical or spiral shape. Okay, so we're learning something. Okay, the reason why I mentioned that I sort of scaffold this talk is because it's very important that we have the basics down, right? Now we're going to take a little bit step further, and we're going to talk about a complication of observing the deep universe, which is actually a good thing, but it's something you have to keep in mind, which is the further away you look in the universe, the further back in time you are looking. Okay? So we like to say that telescopes are time machines, and it's totally true. Because the further away you look, the further back in time you're looking. The reason that works is, so we have the Big Bang, essentially the start of the universe. The universe is expanding with time. It's getting bigger. Okay. Now, when the universe was young, we have these baby galaxies here. Okay, and they're letting their, so essentially in the very early, so time goes down like this. In the very early universe, there are no galaxies. Okay, then you have galaxy formation at some time. All right. These very early galaxies, they will have let the light from those early galaxies will leave them, and it takes a long time before it reaches us, okay? Billions of years, in fact. So by the time we get that light from those really distant galaxies, we're seeing that light from those galaxies as they looked about 13 billion maybe years ago or so. So this would be equivalent to if your family took a picture of themselves, sent it in the mail, the male woman or male man lost it, okay? 20 years later, they find it and they give it to you, and you're like, oh, great, here's my family, from the other side of the country, but that's what they looked like 20 years ago, right? It's the same thing. We're getting old images of the universe because that's just how long it takes light to reach us. So the further away we look, okay, the further back in time we're seeing those galaxies. But that's a great thing, because what we can do then is we can use that to study how galaxies have changed with time as a class, as galaxies as a class, not any individual galaxy, right? But as statistically as a class of galaxies, we can say galaxies when they're young look like this. Galaxies when they're middle-aged look like this. Galaxies in the local universe, which are now old, about 13.8 billion years old or 13 billion years old, like the Milky Way, we look like this. So we can study how galaxies were born, how they lived, changed, and how they came to become galaxies like the one we live in, where we can have life and we can think about this sort of thing, right? Okay. but it gets even better, all right? One more complication is this thing called cosmological redshift. Now, what's happening is after the Big Bang, the universe was expanding, right? And the light's going through the universe, right? Light's a wave. It's also a particle. It's going through the universe, all right? And as the universe is expanding, what's happening is as the space itself is expanding, it's stretching the light, right? So think of light as a wave. It's stretching the light, so the light gets longer and longer wavelengths. So does anyone know what that does to the color? Makes it red, okay? Hence the name, redshift. It makes it red. So when you get longer wavelengths of light, it turns the light red. Now, I told you at the beginning, when we look in the nearby universe, we can notice that the galaxy colors are associated with the types of stars in those galaxies. Okay, blue stars, red stars. When we look at the distant universe, it's more complicated because we're not seeing the galaxy color as it really is. We're seeing it after that light has been redshifted. Okay? And in fact, the further away the galaxy is, the more it's been redshifted because the light's been traveling through the universe longer. Okay, so just an illustration of this. This is just, so this grid pattern here is on the bottom is space, and we will see if this works. Maybe not. Oh, there we go. There we are. All right. Okay. So you get an idea, right? Light leaves blue, but it's being stretched by the expanding space. By the time we observe it with Hubble, right, and then it just goes away. All right. By the time we observe it with Hubble, right, it's been redshifted. Yeah.
I mean, I understand that it's stretching the wavelength. Does it also stretch the amplitude of the wave?
No. Just the wavelength is being stretched. Okay. All right. So we have that to deal with, and I want to bring that up because this is what we see. So we're taking a cut now. Say you did this experiment and you only pulled out spirals from different spirals that were nearby, far, and very far. Okay. And for spirals, you know, we have something like this where very far they look redder, smaller, and you know, as they get nearby in the local universe, it's more like what you see. Now again, what we know from many studies is that in fact this redness is almost entirely due to the cosmological redshift. In fact, these are highly star-forming galaxies in the early universe. There's lots of star formation typically going on for these particular galaxies. So they are actually very blue. Okay. The fact that they look more disorganized is a reality. I mean, they look a little bit lumpy, not quite as pristine of spirals. That's sort of what we see with young spiral galaxies. And as time goes on, they tend to look more irregular and pristine and get bigger with time and more massive. Okay. So we can see that cosmological redshift here. We can take that into account. If we know their distance, we can do what we call de-redden it. So we can, essentially in our computers, we can take away that effect so we can see what the colors it would actually be. Okay. Now what I'm going to do is, that's a primer on the deep fields. I'm going to kind of go through the next few slides just to finish up the Hubble deep field story as it exists pretty quickly. So we have the Hubble Ultra Deep Field from 2004. Okay. What I want to point out is this region of the Hubble Ultra Deep Field, there was a follow-up study. So there was another servicing mission done. Okay. And what astronomers realized, right, is that if you want to capture the most distant galaxies, okay, they're going to be really redshifted. In fact, they're going to be so redshifted that they might be redder than the red color that we can see in visible light. Does anyone know what type of light is redder than visible? Infrared, okay. So we might need to go into the infrared to see the most distant ones because they might be cosmologically redshifted to such a degree. All right, and so in the last servicing mission 2009, they put on an instrument that could detect in the infrared, and they observed this. The instrument has a smaller field of view, than the earlier one, so it sees a subsection of this, and this is what you get. This is the Hubble Ultra Deep Field in 2009. Here's the PI Garth Illingworth. And we're starting to see deeper. We're starting to see more really faint red galaxies pop up. Just so you know, we followed that up with even more infrared observations with the same instrument. And in 2012, we have another version. Now, when I say another version, what I mean is what they've done here is every time they've gone back and done an observation, they've added that data to the previous data. Okay? So this includes all the information from 2009 and 2004 in it, but they've added more. Okay? So we go deeper. And that's what you can do in astronomy. You can just simply add on the more information, the more light that you get. Okay? So in 2012, we have more infrared data of the Hubble Ultra Deep Field. In 2012, we also added on the extreme deep field. So the extreme deep field actually included all of the previous Hubble Ultra Deep Field observations of this patch of sky, plus what Dr. Garth Illingworth and his colleagues did was they went into the Hubble archives and they basically took out any observations from Hubble of that region of the sky and they just added them on. Okay, so it included all the dedicated pointed Hubble Ultra Deep Field, plus if people were doing other science that happened to take observations of that patch of sky, they included that all in. So this was basically the deepest image at the time, 2012, of the universe, of early galaxy formation that we had. And then we come to 2014, and we come to sort of the pinnacle of this Hubble Ultra Deep Field story, where in this one, we've added ultraviolet light to it. Okay. So we have infrared, visible. We added ultraviolet. Ultraviolet doesn't help us see deeper, but it does give us information on what's going on with the star formation process in these galaxies and so on. So we call this the most multicolored view, multiple colors being ultraviolet, visible light, and infrared, the multicolored view of the deep universe. Okay. Now, if you add up all the observations that went into this final one here, you're getting into something like 25 days total of observations for all the pieces that went in to make this, all the previous ones and so on, right? So the original Hubble Deep Field was about 10 days. This is about 25 days, so it's more than twice, plus it's more sensitive instruments, okay? So more than twice the observing time and more sensitive instruments that went into this, all right? Just so you know, if you want to know galaxy counts, I told you that there was 10,000 in the Hubble Ultra Deep Field, okay? This has 7,000. The reason there's less, remember, this is a subset of that Hubble Ultra Deep Field because the infrared camera is smaller. So this is deeper, and it has 7,000 galaxies, but this is the deepest view we have of the universe, of galaxy formation in our universe at this point. Okay, so we see red objects in here. Well, I say these little galaxies in here. Some of them might not even show up on this image that we're seeing back very far, and I'll talk a little bit about exactly how far in a minute. Okay. All right, but I wanted to bring this up, right? We've spent over a decade getting better and better and better images of that patch of the sky, the Hubble Ultra Deep Field patch of the sky, okay? Okay, we also did two other patches, the Hubble Deep Field North, Hubble Deep Field South, the original deep fields, and then the Hubble Ultra Deep Field, which is all these. We did that one patch over 10 years, okay? That's like getting higher and higher clarity images of the same crowd of people, right? Still, the question exists. I mean, it's great. We're starting to really understand the galaxy populations, the young galaxies that we see from the distant universe, the medium age, the nearby galaxies. We're really getting good classification of them in this, groundbreaking science. But the question still exists, is this a special patch of the sky? Okay. And also, how do we go even deeper? Okay. And to do this, we couldn't just keep pounding away at this patch of the sky. We had to have some new thinking. Okay, we had to think outside the box a bit, and that's what we've done with the Hubble Frontier Fields. Okay, PI Dr. Jennifer Lotz. This is a 3-year program. The point of this program is to see deeper than we could with the Hubble Ultra Deep Field, and by the way, in just 3 years instead of the 10 years it took, to see deeper in the Hubble than the Hubble Ultra Deep Field. That's the goal. The goal is also to see more parts of the sky. So we are actually going to look at 6 patches of the sky instead of just 1 for this program. Okay, so just to give you an idea where we're looking, these are numbered. So this is Northern Hemisphere, Southern Hemisphere. These are just the common constellations. You can see where the locations are that Hubble is looking for these. So 1, 2, 3, 4, 5, 6. Okay, as it turns out, we're done with numbers 1 through 4. Okay, so we're really far along. Now the science is not done. The science is just beginning, but the actual observations have been done for 1 through 4. Okay. You'll also notice this little haze. Does anyone know what this haze is? The Milky Way. Okay, good. And you'll also notice that the numbers avoid this. Does anyone know why? It's noisy. So what would be a problem if we looked at the deep universe through the Milky Way? Dust obscuring, right. It's very hard to see the deep universe when you're trying to look past all those stars, all that dust, all that gas, right? So that's why we look outside the disk of the Milky Way for these deep observations. Okay, and the previous deep observations did the same. Okay, now actually, I sort of short-sold it. We're actually getting 12 deep fields, okay? In each one of those locations, we're getting 2 deep fields. The reason we can do this is because Hubble can look at one spot with one instrument. Hubble has multiple instruments on it, and for free, simultaneously, observe a nearby spot with a different instrument, for free. And then later you can swap, so you put the other instrument here and the other instrument here, and so you can complete the set, so you get both spots with both instruments. But basically, the point is that when Hubble has the ability to look at one spot and get free information from another instrument on another nearby spot. And so we're really able to double the amount of deep fields doing it that way. Okay. And just so you know, the 2 instruments we use that one that's really sensitive in the infrared, and we use another one that's sensitive in visible light. So we cover both visible light and infrared. Okay. And I just want to click through these. These are the first 3. I don't think I have the 4th one on here yet. But these are the completed, the first 3. So if you look at these, right, you'll notice one on the left, one on the right, one on the left, one on the right, one on the left, one on the right. If I were to ask you which side, left or right, of these looks like a traditional deep field, what would you say? The right? So what's going on the left? What is different? What looks different about it? There's what? They're more illuminated? Okay. So you see this like haze, this illumination? Yep. It looks maybe a little bit more crowded in aspects of the image. Okay, that's right. So part of the goal of this program is to take more images of the deep universe, and we call the ones on the right, we call them blank fields, not because there's nothing in them, but because they're the traditional blank part of the sky deep fields, like the previous deep fields. Okay, they're sort of repeating the experiment, going almost as deep as the Hubble Ultra Deep Field 2014 in here. They're going not quite as deep, but pretty deep, and you're getting 6 of these traditional deep fields. The ones on the left, we're redoing the experiment, but this time we're purposely targeting not a blank patch of sky, but a very busy patch of sky where galaxy clusters are located. Okay? These are locations in space where galaxies are physically located near each other, lots of them, thousands of them. Okay? And so that's why you see all these galaxies here, and it's not a blurry image. That's the light from all the stars in the galaxy cluster. Okay? All right. So I'll tell you why, but basically the point is that on the right we're getting more locations. On the left we're getting more locations, but it's more that we can use a trick of this to actually see deeper in the universe by looking at these galaxy clusters. So that's what I'll talk about here. So I want to remind everyone with a few videos here how light behaves. So if we have a distant source, right? Light goes in a straight line, but if it hits a big lens, like what you have on a telescope, say, or something, right? That glass redirects the light. All right, that's what it does. That's what it's made to do, to come to a focus so our eyeballs can see it. And so what this allows us to do is to collect a lot more light than we could with our eyeball alone, because it takes all this light that was going to leave and go off in different directions and collects it and puts it on our eyeball so we can see really faint things. That's why we use telescopes, right? That's the point of telescopes, okay? That's what a telescope does. Now we actually use mirrors in modern day telescopes, but it's the same basic concept. So that's what a lens does. Let's see. All right. Now, what's great about about this trick I'm going to talk about is, so what happens is whenever you have anything with mass, what it actually does, like a star or anything, is that mass actually bends space-time itself. Okay? So whenever you have a mass, it actually bends space-time. And what happens is the light is forced to follow the curvature of space-time. So that's what I'm going to show you in this little video. Incidentally, Frank helped make a lot of these, so I don't think he's in here now, but you can. Okay. So you have, there's space-time. You have a star. Okay. The mass of the star bends space-time, and the light was going to go straight, but it's forced to follow the curvature of space-time. Okay. Can you show that one more time? Okay. That's just a feature of having a mass out there, right? A mass will bend space-time. Now this is Einstein's theory of general relativity, and it's been proven, okay, in an experiment. So this is what's happening anytime you have a mass. Okay, so that's great. You have a mass, it's bending space-time. Light is being forced to curve. But how can you bend space-time more? That's what I want to know, right? You have a star. What can do better than a star? A black hole could. A galaxy could. Galaxy's more massive. What's better than a galaxy? Many galaxies, say a cluster of galaxies, say a really high, massive, dense cluster of galaxies like you saw on the left on the frontier fields. So let me show you another video here. Okay. All right. So here is a video. Now, keep in mind, this is a very similar setup to that lens that you saw, but this time instead of a glass lens, you have a galaxy cluster here, which is bending space-time, redirecting the light, and serving as basically the same principle as if you had a big lens out there. It redirects, all that curved space-time redirects the light and gets it to Hubble. Okay? This is exactly why we focused on galaxy clusters. It's because we can use, what we'd like to say is we can use nature's telescope, these big galaxy clusters that will redirect the light for us, in combination with our telescope, Hubble, to see even further than we could if we had Hubble alone. Okay? Because what happens is, just like with a lens, is you are collecting more light from these background galaxies. So in this picture, we have the galaxy cluster, and then we have really distant galaxies that are behind that cluster. And what's going to happen is those really distant galaxies behind that cluster, we're going to see them, and they're going to be magnified. Okay? They're going to be brighter than they would if they weren't being lensed. We call this a gravitational lens. So we have a glass lens that we showed you. This is being lensed by gravity, okay? By the curvature of space-time. Okay? So these are gravitational lenses. All right? And so what you have is, here's the first galaxy cluster that was done. These are just catalog names, so we don't, actually this does have a better name for this particular one. It's the Pandora cluster. But here's a cluster, here's the first cluster. And what you'll see is you'll see all these really bright galaxies that are closer to us that are bending space-time. Now what I want you to do is I want you to look at these. Okay? What's interesting about gravitational lensing is, when you have a lens, when you make a lens for a telescope, you polish it, you make it perfect so that everything comes to a nice focus. The universe doesn't do that for us, right? This gravitational lensing, the light takes different paths as it follows the curvature of space-time. All those light rays don't necessarily meet up together, right? So what you have is you have a funhouse mirror effect. Okay? This galaxy right here is the exact same as that galaxy. It's the exact same galaxy. That's the exact same galaxy. All these orange ones, that's the same galaxy. It's not three different galaxies, it's the same galaxy. We're seeing that same galaxy in three different places on the sky. Okay? Same with this one. That galaxy is the same as that galaxy is the same as that galaxy. The exact same galaxy. The reason that works is because those are distant galaxies behind the cluster. As the light leaves that galaxy, the different light paths are hitting different curvatures in space-time from the galaxy cluster, and they're all following slightly different paths to get to us. By the time those slightly different light paths get to us, they don't all match up in the same physical location on the sky. Some might get to us and it might look like the galaxies here. Some might look like the galaxies here. So these galaxy clusters are playing funny things with the light. Okay? But it's not a bad thing, right? We actually have three versions of this galaxy, okay? And again, what's really great about it is that these galaxies are magnified. They're brighter than they would have been, okay, had they not gone through gravitational lensing, all right? And so we can use that. The other good thing to know about this, we talked about colors of galaxies. The colors of galaxies do not change if they're gravitationally lensed. The colors stay the same. These are the colors, these are exactly the same colors as the original galaxy. Now they're warped, the shapes are warped, they look a little strange because the light paths took different paths to get here. But the colors are exactly what they were. Okay, now I wanted to take a step back. If any of this sounds familiar, how many people were with us last year? Okay, a lot, okay. If any of this sounds familiar, we did this last year. Well, I wasn't here, but Frank did this with you, and several of you did this last year, John. Where you did this, we're talking about modeling and how you can model things in the classroom. This is one way last year where you guys modeled this gravitational lensing, okay? Something that you could do in the classroom, where we had the materials, right? We had these different glasses, and you hovered them over this grid sheet, and you notice how when you tilted the glasses, the grids took on different shapes, right? It could be curves, it could be basically the light passing through that glass took different, caused the light to do funny things, essentially, right? Curved shapes and so on. I mean, you can kind of see that here with the stem of a wine glass and a candle. You can see ways where you can create multiple images of that candle or a circle. Here's an actual Hubble image of gravitational lensing of a galaxy that's basically the same concept as that, where that's one galaxy, a very blue distant galaxy that's gravitational lens to look like a curve. Okay, so this is something that you've basically done, and we showed you how you could sort of find a way to model this in the classroom last year. Okay. All right. So I imagine that when we started this and I was showing nice pictures of people on planet Earth, you thought, oh, this is going to be easy. I can zone out. Okay. This is getting more and more complicated because what we're doing is we're going to take it a step further. I've talked about the observations. Okay. We can't do anything with the observations if we don't have people that know how to model these observations, know the physics behind general relativity, and how we can use models to help us explain what we're seeing. So what I'm going to talk about in the next few slides are sort of we have astronomers on staff that do the observations. We also have astronomers and mathematicians and physicists and modelers that help us with the modeling, to help us understand what we're seeing. We're going to talk about the modeling. Okay, here is that same galaxy cluster. Now this time we put some funny colors. So in the background you can see the same image. It's in green this time, but it's the same image. This time what we've done is we have ways to estimate the mass of the cluster. Okay, we can count up how bright it is and get an estimate for the amount of stars in there, which gives us an estimate of the mass. Plus we have an estimate we can do an estimate based off of the lensing we see of how much invisible dark matter. Basically, all the matter in there, we can estimate. It's not perfect, but we can estimate it. And we can basically create a map of the concentration of mass that's doing the bending of space-time. And that's what you see in blue. Okay, this is a model, okay, an estimate of the mass in blue. So you can see where it's really blue, it's locations where there's lots of galaxies. That's where it's really bending space-time. But you can see that there's still some curvature of space-time out here. There's still some of the cluster out here. There's a little hazy blue. So there's bending. Once you know the mass, and you have a model of the mass, okay, then you can model how much brighter a distant galaxy will look based off of where it's located in the image. And that's what this pink thing is here. So basically, these are the max, anywhere near these pink lines here are where you're going to find maximum magnification from gravitational lensing from a distant galaxy. Okay, these are all models. These are all things that we have to do. All right. So if you find a distant galaxy that appears to be gravitationally lensed here, you'll think, okay, it's going to be really magnified. And also, when you know where it's located, you can try to figure out. You can try to use these. We call these curves. You can try to use these curves to try to find out where its other versions of that same galaxy might be located in the image. Okay. All these are models, right, to figure out how magnified are those distant galaxies, are there multiple versions, and so on. We're really, again, what is the point of all this? We're really trying to find the most distant, faint galaxies that might be the earliest galaxies to form after the Big Bang. We really want to get a picture of those baby galaxies because we have pictures of basically galaxies at all of their lifetimes, but not the first baby galaxies, right? How do galaxies start? Okay. Okay. Now, it gets a little bit complicated because this pink curve is actually the model for galaxies that are at a certain distance behind that cluster. Okay? If a galaxy is at a different distance behind that cluster, you have a different pink curve. So every distance behind that cluster, you're going to get a different model for where it's going to be magnified. So they run the point of saying that is they run lots of these models, and they run lots of these models to look for galaxies that are at different distances behind the cluster. And then they try to use that to match up with what they see, where they appear, and so on. And what they did was they did this, and they found in this image a really distant galaxy. And so this was one of the first frontier fields results. So in image A here, or in box A, they actually found this just by eye, incidentally. They said, oh, here's a red blob. Its colors look like it should be a really distant galaxy, okay? But they didn't know if is it really a distant galaxy, or is it just happen to be a closer galaxy that just happens to be red, right? Is it redshifted? Is it a distant redshifted galaxy, or is it a nearby galaxy? Well, just by looking at the colors, they ran their models just from the colors, and it said it's likely a distant galaxy, but we can't be sure. The only way to be sure is to run those models I just showed you. They had an estimate. If it is a distant galaxy, they know which pink curve to do. They know how far it would be. They know which pink curve to run. So they ran the experiment. They ran these curves. And when they did that, they came up with an estimate for if it is a really distant galaxy, where would it also appear in the image? Okay, they ran that model. And what they did is they ran it, and that's how they found B and C, which confirmed that it was a really distant galaxy. How distant? This galaxy, we're seeing it. This galaxy, the light from this galaxy takes about 13.2 billion years to reach us. So we're seeing this galaxy as it existed about 500, 600 million years after the Big Bang, a very infant galaxy. In fact, if it's about 3%, when light left this galaxy, the universe was about 3% its present age. So if you had a picture of if you had a friend that was 100 years old, it would be like getting a picture of when they were 3 of that person, right? So it kind of tells you that that's really reaching deep into the universe. This is one of the deepest images of a galaxy we have, okay? Okay, so that was a good success, and it tells us that our models are working. Of course, I should put a caveat. Our models always need to be improved, and I'll show you how that works. So we're talking about the same result now, where they found those 3 galaxies, and the way it works with the models, just to give you some idea, is if they have a galaxy, here's the galaxy cluster, and if they have a galaxy here, okay, they'll know that, okay, the light bends this way and gets to Hubble, and they should see it here and here, for example. This is just a sketch, just to give you some illustration. The point of this is, if the galaxy is actually further, right, the way that the lensing works is that the lensing works like this, is that they will see the galaxy here and here. They'll see it at a further separation, okay? So the further away the galaxy is, the further they'll find them separated on the image, okay? That's just the way that the geometry of lensing works. If the galaxy is nearby, they'll see that the images of that galaxy they actually observe on the image are closer. If the galaxy is far away, the images they actually observe on the image are further away from each other on the image. And so getting back to that result I showed you where they found A, B, and C galaxy, they ran the models. They estimated that A, just don't worry about these numbers other than the bigger the number, the further away the galaxy should be. These are the models. They thought A should be at around an 8 or a 9 here, okay? And then they found that B was around an 8 or a 9, and then they saw that C actually fell off the charts, okay? What does this tell you? Yeah?
Oh, sorry.
No, go ahead, ask your question.
Because it's such like a complex system, and
Yeah.
the models, when you run them, you have to run them like assuming so many different distances. Is this the kind of thing that you will look to for like large supercomputers?
There are some uses for this in supercomputers, or at least, if not supercomputers, large clusters of computers working together, yeah. So you do need a lot of computation time for this. And in the case of that particular one galaxy, what they did was they had an estimate for what its distance was, and so they can run the models that are around that distance. So that narrowed the models down. But if you're just sort of doing a fishing expedition, as you call it, you don't have a galaxy to go after and you're just looking for anything, you would have to run a lot of models and you would need to use a lot of computational power, yeah. And incidentally, this falls off the scale here. What this tells us is that we have still a lot of uncertainties in our models. Okay, that's what that tells us. There's still a lot of uncertainties. The way this works, right, is we have the models, and for this team, there were actually 6 competing modeling teams around the world that got together and actually worked together, and they gave us 6 different models. So I told you that there's different models for different distances, but there's also 6 versions of those because there's 6 different teams. They're all doing their own models. Okay, you can start to see it's getting complicated, right? And what we're trying to do is we're trying to understand, the reason why they have slightly different results from the different teams is because they assume slightly different physics, slightly different geometries, and so on. But where we have situations like this, we can test the different models to see which ones are getting us the most accurate, and that will tell us which ones are assuming the proper physics, and it helps everyone make their models better. So this is a cyclical process, right? This is a process where we went in having some models, we got the observations, they're running their models. Their models are doing a good job, but there's still some problems. So from the observations and from results like this, we go back in, people change their models, they get better models, and we go from there, okay? And I just want to show this is a really cool result this happened earlier this year. This is another galaxy cluster from the frontier fields, and what you see here is one supernova that went off, okay? But you're seeing it 4 times, okay? So what is actually happening is this yellowish orangish blob here is actually a galaxy in the galaxy cluster, and it happens to fall in front of a background spiral galaxy. You see that blue thing where one of the spiral arms happens to fall behind, and you're seeing that spiral arm lensed around that foreground galaxy cluster, or that galaxy, and a supernova happened to go off in that spiral arm. So not just the spiral arm is being lensed all the way around, but that supernova is lensed 4 times all the way around. And so they actually found that the different light travel times of that supernova, they think that this one arrived first, then this one, then this one, then this one. Okay. Now, what's even cooler than that? And this was actually proposed that this is something that should be observable, and this is the first time that this has been observed, to see a lens supernova like this. What's actually cooler is that they ran their models. This distant spiral galaxy is actually also here and here. And I don't remember which is which, I forget. But in one of these, we estimated that the supernova already arrived. But in the other one, it should arrive in about 5 years. It's like getting a rerun of a TV show, right? That same supernova, the light from that same supernova is taking different paths to reach us. And we will see it in about 5 years from, yeah.
The really red galaxy before, you said that they estimated the distance they had some place to start with.
Yeah.
How did they get that estimate?
So what they've typically done is they've used, it's called a photometric redshift, which just means they use colors to estimate its distance. And what they typically do is they have various filters on that they observe with that object with, various colors. So they look at it, very different colors. And from the combination of the different colors, they've done models and they've done experiments locally and shown that they can fairly accurately estimate the distance just off the color. So if there's, like, say 30% more red in this color than in this color, or 30% more light in this red color than, say, in this green color or this blue color, you know, the ratios of light in the different colors can give you an estimate of the distance from the redshift, okay? It's called photometric redshift, but it's not perfect because there are some overlap, there's some overlap in the answers, and you could conceivably get nearby redder galaxies that could also be the answer to those colors. So that's it's not the most accurate way, but it's the way that they typically do these high redshift galaxies. The best way to just nail down the distance, if it's near or far, is to take a spectrum of that galaxy, to break up the light in its component colors, look for features in that light, and that will tell you if it's redshifted or not. But with these really distant, faint galaxies, you can't do that because you're breaking up that little amount of light you get into even less light, and it's too faint. So that's how they typically have done it. But with these lensing models, it's a third way. So we have spectra, which is great. We have the photometric redshift, just using the colors of the objects, which has been okay. This is a third way. It's a geometry problem and a lensing problem that actually can help confirm, using with the colors to confirm if it's distant. So I want to leave with this. With the frontier fields and the Hubble Ultra Deep Field, we are getting to these toddler galaxies. We are starting to understand. We are starting to understand some of the earliest galaxies in the universe. Okay, but we still can't, even with the frontier fields, we still can't go as deep as we would like. Okay, so we need a more powerful telescope. Does anyone have any idea what that might be? James Webb. Okay. We need the James Webb Space Telescope, a dedicated infrared telescope that's very sensitive in the infrared. And one of its primary science goals is to measure what's called first light, which by this we mean the light from the very first galaxies and stars to form after the Big Bang. Okay, it's going to look back even further. And with James Webb, we should be able to, essentially like peering in the nursery in a hospital if you're in space looking at humans, we're going to basically be looking for the very newborn galaxies. Okay, so we can, just like how, if any of you are parents, I'm sure some of you are, just like you'll notice with your kids, the most changes that you'll notice a human being undergoes in their lifetime is in the first 2-3 years of their life. It's amazing, right? Same thing we think with galaxies. We think that the most changes a galaxy, we hypothesize that the most changes that a galaxy undergoes is early on in its life. Okay, and that's what we're trying to test. All right. Okay, and just so you know, additional resources, we have more information about this on our Hubble25th.org. You're probably already getting some of this. Hubble25th.org. We also have a dedicated public blog about the frontier fields where you can find more videos and more things about this, frontierfields.org. Okay, so I'll leave it there. All right, so are there any questions? I'm sure.
I have a question.
Yeah.
Do you have to go really that deep in time to look at infant galaxies? Can't you do it a little bit closer in time? Because you said if you have a friend who's 100 years old, you wanted to see how he looked when he was 3, yeah, you look at a photograph. But if you wanted just to see what humans look like, can't you just look at babies being born?
That's okay. So great question. So you have pinpointed where my analogy breaks down. Okay, which is great because all analogies break down at some point, right? So, right, in this analogy, you could say, why do you have to look back so far? Why don't you look nearby for a baby galaxy, right? The problem is that there are not, we do not find any completely pristine galaxies in the nearby universe. Okay, we do find some that are getting close, but the problem is, as the universe has evolved from the Big Bang, galaxies have done star formation and undergone star formation, and they've basically, there's a lot of effects, but one of the effects is when you do star formation, you actually make heavy elements in the periodic table. Most of the elements above hydrogen are made in stars. So what happens is when stars make those elements, and they start doing that right off the bat in the early universe, they die, they pump those elements back out into space. All that material, that enriched, we call it enriched material, doesn't just stay in the galaxy, but it gets spread out through intergalactic space, and other galaxies pick it up, and they're sharing material, and they're becoming enriched. So even if you had a pristine galaxy that did not do much star formation yet and represented the earliest galaxy of the universe, it's still picking up material from other galaxies that have done stuff. It wouldn't be as clear. It's undergone effects, gravitational effects probably too, throughout its lifetime that might distort the story. Also, there are certain types of stars that just don't exist anymore in the universe that we suspect existed in the early universe. We call these type 3 stars, but they're really giant stars that we're looking for that we think basically did the first enrichment of the universe. And we don't expect to find them in the nearby universe, but we expect to find them in the early universe with the first galaxies. So there's some things that are just, you have to go and look in the distant universe. But that's a great question. Okay. Are there any questions? Yeah.
conceptually, when I start to think about all this, it kind of hurts my head.
Yeah.
In that if we're looking back so far, how are we, like, where are we in the universe that no matter what direction you look, you're peering into the very beginning of the universe? In my mind, I would think that that very beginning should kind of be somewhere.
Nope. That's a great question. And this is one of the fun parts and difficult parts about cosmology is that our brains have a difficult time wrapping around this cosmology. The thing to remember, now Frank has talked about this before, he likes to say that if you think about the Big Bang, you think about the Big Bang as a time, not a location, okay? There's many ways, well, not many, there's a few ways you can think about the Big Bang, the start of the universe, but basically everything came from the Big Bang itself. It was an event that happened about 13.8 billion years ago. Okay, it was an event. All time and space came from that event. Okay, everything came from that event. And so when you look around today, everything is a part of that event. We're all basically the center of the universe. There's no center place you can go because we all came from that event, right? And conceptually, it's hard, I understand. And part of the problem is that when we teach this, we use analogies because you have to, right? Because it's difficult. And sometimes our analogies break down. Like one common analogy, one analogy people like to use is you blow up a balloon, right? You mark points on the balloon. Those points represent galaxies. You're blowing up the balloon, and you can see, oh, the galaxies are getting farther apart, not because the ink dots on the balloon are just moving away, but it's because the balloon itself, space, is expanding. And so no matter what point you are on that balloon, you're going to see all other points moving away from you because space itself is expanding. Okay? There's no preferred place in the universe where that wouldn't be the case. But the problem with that analogy is just that. Then someone is going to ask, okay, well, what is the balloon is expanding into the air in this room? What is the universe expanding into? Or there's air inside the balloon. What is the shape of our universe and what is inside? So these are all conceptually difficult things, and you know, I don't know if I've ever come up with that's how exactly you picture it, because again, these analogies break down. I will say in terms of the shape of the universe, that's still an open question, but we're coming down to some consensus, and you can think of the universe as different shapes. But again, it's tough because when we say shapes, we mean all four-dimensional space-time is on a shape, which is hard for your brain to wrap around, right? So, I mean, it's a great question. I don't know, Frank, if you wanted to try to... I always go to him because I feel like you need maybe a different way of explaining it sometimes to...
What you really need is some beer. Okay? Because when you take that balloon analogy, okay, and you're really thinking, okay, you're representing a two-dimensional surface expanding into a three-dimensional volume, right? But when you have to think of the universe as a three-dimensional volume expanding into a fourth-dimensional volume, right? And you can't imagine four dimensions, right? No matter how much beer you have, unfortunately, you have enough beer you think you can imagine four dimensions, but you can't imagine. And so you really have to recognize that it's the fabric of the universe expanding, right? And so I like to go take down even smaller down to one dimension, because it's something you can do in the classroom with just a simple rubber band and dots on a rubber band and pulling up one dimension, and seeing that, hey, you've got these things, and if the rubber band is the space, you don't think of it, you make sure that you think of that the galaxies are not moving through space, but the space itself is getting larger.
Mm-hmm.
It's Brandon and I are standing still, but we appear to be going further apart because the space is getting bigger between us, right? And that's kind of a freaky idea, isn't it? But that's truly, truly what we see on large scales in the universe. Like Andromeda and the Milky Way, they're gravitationally bound to each other. They're going to be colliding, and the local group is gravitationally collapsed. So within the local group, that's not happening. But between here and the Virgo cluster, we appear to be getting a little bit further away. Eventually we'll collapse in, or between us and the Virgo cluster and the Coma cluster, it appears to be getting further away. but they don't have to be moving, it's just the space getting bigger between them.
So is there an issue where we can't see far enough away from ourselves to notice a difference between the amount of space that is expanding between ourselves and the Virgo cluster and then other clusters? Shouldn't we be able to figure out like geometry pointing back to?
No, but if every space, if all space is getting bigger, there is no center to any of that, okay? Because it's as if space between the two of you gets bigger, right? And space between the two of you gets bigger, he's moving away from you twice as fast, but, you know, you see everybody moving away from you. And she will see everybody moving away from her, and he will see everybody moving away from him. And so there is no special point in that universe, right? That everybody sees the same thing, and that is actually one of the arguments in favor of this model, is that we should not exist at any special point in the universe, right? The idea that we have some cosmic cooties and everybody's running away from us, get away from the Milky Way, all right, is kind of ridiculous, right? All right, we're not in 5th grade anymore. You guys unfortunately don't have to teach 5th grade. But the idea, so if we were at the center of the universe and everybody was running away from us, that would be really unusual. All right, it violates the Copernican principle. Whereas this model of the universe expanding allows us to say, okay, well, if we see it, and people in Andromeda see it, and people in Virgo cluster see it, and people in the Coma cluster see it, well, then that's what we should see. And so that philosophical shift of space expanding really allows you to give a what feels like a much more scientifically satisfying answer out of what is a strange idea.
Yeah. My favorite, actually, I don't like the balloon as much. The raisin bread I like a little bit better. So if you imagine plain dough with raisins in it and you put it in the oven, and dough represents space, raisins represent galaxies. And you'll notice as it grows, right, that the space is expanding. The raisins are all moving away. No matter which raisin you lived on, you would see all other raisins moving away. Okay? Again, because all space is expanding. There's still some problems with that analogy, but that's basically the point. And I actually thought you were going to ask a different question the way you started it, but there is this issue of, right, what is the limiting, what limits us to how far back we can see? And that really is basically the amount of time that light takes to reach us, which is a time factor is the limit. We can see back to essentially close to the Big Bang, as close as we can, right? But you could ask, is that how big the universe is? No, right? As we've been waiting for that light to reach us, the universe has not stopped expanding, right? So we talk about the observable universe, which is how far we can see, because that's how far light has had time to reach us. But all these galaxies in the meantime have been speeding away from each other and are much further away from us than they are when their light left them to reach us, right? So there's the observable universe, which is how long the universe has been around, how long light has had time to reach us. That's how far back we can see, or how far away we can see, right? But then there's the actual universe, which carries on beyond that, which has an estimated size. But that's even further, because light has not had time from those things yet to reach us. So it's a very complicated, yeah.
What kind of objects would we see then that would have a blue shift?
Okay, so what kind of objects would we see have blue shift? So blue shift, redshift is so cosmological redshift, right? There's no such thing as a cosmological blue shift, okay? So blue shift is when the wavelengths of light shrink, right? So redshift, you stretch the wavelengths. Blue shift, you contract them. There's no such thing as a cosmological blue shift. We also talk about a redshift in terms of if a galaxy is physically speeding away from us, not just from the expansion of space, but its actual motion. If there's motion of that galaxy that's moving away from us, that causes like a Doppler effect. It causes a redshift of light. There is an equivalent to that's blue shift, where if a galaxy is moving towards us, okay, if it has some velocity towards us, minus the expanding space, if it's moving towards us, it will exhibit a blue shift. And that's only for the things that are so close to us that gravity has won out over the expanding universe. Okay, so we see a blue shift for Andromeda. We see a blue for the Andromeda galaxy and the other local galaxies, or most of the local galaxies. So, okay, I think we are well overdue. So This always elicits a lot of questions. I'll be here the rest of the day if you have any more, but I think it's lunchtime, so, okay, thank you.